prove that the path difference between two secondary wavelets reaching at a point, the path difference between two secondary wavelets reaching at a point in a medium is a sin theta is equal to n lambda by 2 for nth secondary minimum. Prove that the path difference between two secondary wavelets reaching at a point in a medium is a sin theta equal to n lambda by 2 for nth secondary minimum obtained on a screen due to diffraction of light. In the diagram, AB is a narrow slit or aperture and parallel rays are incident. On the aperture or the narrow slit AB. This is the parallel rays, and these parallel rays are actually refracted through a convex lens as shown in the figure. This is the convex lens L1 through which parallel rays are coming, and that parallel rays will be incident on the aperture AB. And here we can denote the screen on which this rays will be incident, and a source of light is placed at the focus of this convex lens L1, and from that source of light S, rays are diverging, and that diverging rays are incident on the convex lens L1. S be the point source of light which is placed at the focus of the convex lens L1. S is the point source of light, and this point source of light is placed at the first principal focus F11 of the convex lens L1, and through the convex lens L1 incident rays are coming. These are the incident rays which are parallel to each other, and that parallel rays coming from the convex lens L1 are incident on the aperture AB, and we can place another convex lens L2 in front of the aperture AB. This is the convex lens which is placed in front the aperture AB, and L2 is the convex lens which is placed in front of the aperture AB, and it is also, and rays are diffracted at the sharp corners of the aperture AB along this direction. These are the secondary wavelets or diffracted ray or rays which will bend at the sharp corners A and B along this direction. This is the direction along which secondary wavelets will be moving, or diffracted rays will be moving along this direction. That means at the sharp corners A and B of the aperture AB, light will bend. Finally, after refraction through the lens L2 or through the convex lens L2, refracted ray will meet at the point P on the screen. This is the ray or secondary wavelets. After diffraction, secondary wavelets will be refracted through the convex lens L2, and from the convex lens L2 diffracted rays will be converging. They will converge and they will superimpose at the point P1, and AB is the aperture, and AB is also the wavefront, plane wavefront. From plane wavefront, secondary wavelets, parallel secondary wavelets will be traveling along this direction, and this secondary wavelets will be diffracted at an angle theta, and without any diffraction or deviation, parallel rays will be refracted through the convex lens L2, and they will converge and meet at the point O on the screen. So these are the rays which will be converging after refraction through the convex lens L2, and they are not diffracted, but these secondary wavelets will be diffracted at an angle theta. That means rays at the sharp corners A and B will bend at an angle theta with the original direction, and these are the secondary wavelets which are diffracted. Now we can denote different points on the aperture of the convex lens L2. A1, C1 and B1 are the different points at which the secondary wavelets will intersect the aperture of the convex lens L2. And finally, secondary wavelets after refraction through the convex lens will superimpose at the point P1 or will reach at the point P1 or will converge at the point P1, and at the point P1 we get dark fringe or first secondary minimum. Similarly, in the lower portion we get secondary minimum, and in this region we get central maximum. The diffraction pattern will be central maximum in this region around the point O on the screen, and the central maximum will have the order n equal to 0, and and this is the bright region. Central maximum means bright region, and at P1, around the point P1 we get first secondary minimum or dark fringe having order n equal to 1. Similarly, in the lower portion of central maximum at the point P1 prime we get another first secondary minimum having order n is equal 1. Let S be the point source, let S be the point source of light which is placed at the first principal focus, F11 of a convex lens L1, such that parallel rays emerge from the convex lens L1 and incident on the narrow slit or the aperture AB or the aperture AB of width A. A is in the diagram, A is the width of the narrow slit or the aperture. Small a is the width of the narrow slit or the aperture. Capital D is the distance of the screen from the aperture. F is the focal length, and F22 is the second principal focus of the convex lens L2. And this parallel incident rays deviate from the sharp corners A and B of the narrow slit or aperture AB at an angle theta from its straight line path. Hence, these diffracted rays are incident. At the points A1, C1, B1. That means A1, dot 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 C1, dot 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 B1 of the aperture of the convex lens L2. And converge at the point P, at the point P1 on the screen. These diffracted rays will converge at the point P1 on the screen after refraction through the convex lens L1. The second principal focus F22 of the convex lens L2 to form first secondary minimum. These diffracted rays converge at the point P1 on the screen such that the screen is placed at the second principal focus of the convex lens L2 to form the first secondary minimum at that point. Now we can draw a perpendicular from the sharp corner A of the aperture AB on the secondary wavelet BB1. AN is the perpendicular from the sharp corner A on the secondary wavelet BB1, and we can assume BN as 2 lambda by 2. As Bn is 2 lambda by 2, that's why the aperture AB can be divided into two parts, AC and CB. Aperture AB can be divided into two parts, AC and CB, and this length of this part or length of this straight line cm will be 1 lambda by 2. The path difference, the path difference, the path difference between the secondary wavelets, the path difference between the secondary wavelets AA1 and BB1 from the wavefront AB under bracket, that is the aperture, the path difference between the secondary wavelets AA1 and BB1 from the aperture AB, that is the aperture, reaching the point P1 on the screen such that uh, delta x is equal to BB1 plus B1P minus what? What will be the path difference between the secondary wavelets AA1 and BB1 reaching the point P1? This is the path traveled by the secondary wavelets BB1, and the path traveled by the secondary wavelets AA1 is this path. That means it should be minus AA1 plus A1P, or comma delta x is equal to only Bn, or comma delta x is equal to AB sine theta. Therefore delta x is equal to small a sine theta, such that the aperture AB or width of the aperture AB is equal to small a. Delta x is equal to a sine theta. That is the path difference. That is the path difference between the secondary wavelets, diffracted from the sharp corners of the aperture AB. Delta x is equal to a sine theta, which is the path difference between the two secondary wavelets. Let Bn is equal to 2 lambda by 2, where lambda is the wavelength of light, and Bn is equal to 2 lambda by 2 for first secondary minimum. As Bn is equal to 2 lambda by 2, that's why the aperture AB is divided into two equal parts AC and CB. As Bn is equal to 2 lambda by 2, that's why the aperture AB is divided into two equal parts AB, AC and CB, such that CC1 is equal to 1 lambda by 2. Bn is equal to 2 lambda by 2 and CC1 is equal 1 lambda by 2. The path difference. So here the path difference between the two secondary wavelets, CC1 and AA1 from the point C and A, of the wavefront AB is given by the path difference between the two secondary wavelets CC1 and AA1 from the sharp corners C and A of the wavefront AB is given by delta x is equal CC1 plus C1P1 minus AA1 plus A1P1, that is equal to only Cm. Therefore delta x is equal to 1 lambda by 2. That is the path difference between two secondary wavelets CC1 and AA1 reaching the point P1. Delta x is equal 1 lambda by 2. That is the path difference between two secondary wavelets CC1 and AA1, and delta x is equal to 1 lambda by 2, which is the odd multiple of lambda by 2. That means the odd multiple of half of wavelength of light. As delta x is equal to 1 lambda by 2, that's why for every point in the upper half of the aperture AB or wavefront AB, for every point on the upper half AC of wavefront AB, there is a corresponding point in the lower half CB, in the lower half CB of the primary wavefront AB. This is the upper half, AC is the upper half, and there will be lower half. Lower half. If we consider a point in the upper half, there will be corresponding point at the same distance in the lower half CB, such that the path difference, between the secondary wavelets originated from the 2 points in the upper half and the lower half, or lower half, reaching the point P1 on the screen, after refraction of light through the convex lens L2, will be lambda by 2. That means wavelength of light divided by 2, that is the odd multiple, of wavelength, that is the odd multiple of lambda by 2, therefore delta x, finally delta x is the path difference between two terminal secondary wavelets CC1 and AA1 is equal delta x, which is given by 2n lambda by 2. So for constructive interference, delta x is equal to 2n lambda by 2, and we know that for destructive interference, path difference delta x will be 2n minus 1 lambda by 2. That means the path difference between two secondary wavelets satisfies the mathematical condition for destructive interference. Delta x is equal to n minus 1 lambda by 2. That means the two secondary wavelets will form dark fringe at the point P1 lambda by 2. Then destructive interference occurs. Thus destructive interference takes place. At the point P1 on the screen, and as path difference is odd multiple of lambda by 2, that's why destructive interference takes place at P1, and therefore P1 is a point of first secondary minimum. If we consider a secondary wavelet from the upper half of the primary wavefront AB, there should be another secondary wavelet coming from the lower half, such that if they superimpose at the point P1 on the screen, path difference between the two secondary wavelets is delta x will be equal to 2n plus 1 lambda by 2, that is odd multiple of lambda by 2, and dark fringe will be formed. So here obviously these two secondary wavelets will form dark fringe at the point P1, and similarly if we consider two secondary wavelets coming from the upper half and lower half of the wavefront AB, they will form dark fringe. That means destructive interference will occur. Therefore delta x is equal to 2 lambda by 2 for first secondary minimum. This is the path difference between two extreme secondary wavelets BB1 and AA1. Again delta x is equal to a sin theta. Therefore a sin theta is equal to 2 lambda by 2. A sin theta is equal to 2 lambda by 2. That is the path difference between two extreme secondary wavelets or diffracted rays BB1 and AA1 from the sharp corners A and B of the aperture AB. A sin theta is equal to lambda by 2. This is the path difference between two extreme secondary wavelets BB1 and AA1 for the formation of first secondary minimum. Therefore, for nth secondary minimum, the path difference between the two diffracted light waves, or between the two secondary wavelets, for nth secondary minimum, a sin theta is equal to 2n lambda by 2. A sin theta will be equal to 2n lambda by 2. This is the path difference between two secondary wavelets for having nth secondary minimum at the point P1 on the screen. So we get a sin theta as equal to n lambda by 2, where the value of n starts from 1, not from 0, where n starts from 1, n equal 1, comma 2, comma 3, comma dot 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 dot. A sin theta, we get a sin theta as equal to 2n lambda by 2. So this is the path difference between the two secondary wavelets for nth secondary minimum, which is given by a sin theta equal to 2n lambda by 2. This is the path difference between two secondary wavelets for nth secondary minimum. Nth secondary minimum. A sin theta is equal to n lambda by 2. Similarly, the path difference between two secondary wavelets for nth secondary maximum is a sin theta is equal to n plus 1 lambda by 2. A sin theta is equal to n plus 1 lambda by 2, where n starts from 1, 2, 3, dot 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 dot.